Like Dylan mentioned, my name's Austin Ellsworth from Weller Truck Parts. I run the infrastructure team there, where we manage everything related to servers, storage, firewalls, networking. So you can see how HAProxy fits in there pretty easily. I'm excited to talk about our most recent project, which I'm very passionate about, and it is Subsecond data center failover, and it's how we are revolutionizing our team's uptime using HAProxy. Plan for this talk, I'm going to go into some of the business-related decisions behind this project, and I'm also going to show you how we implemented it. So we'll do a technical overview, but also dive into some of the configuration. If this seems like a deployment that might fit your company's architecture or model well, I'm going to show you how to do that in about 12 slides. We also have a couple really cool demos that I'm excited to show today. One of them will be live in our production environment. So a little bit about Weller Truck Parts. We are the largest heavy-duty truck parts remanufacturer in all of North America, actually. What we do is we provide some of the largest freight companies with things like differentials, transmissions, steering gears, drive shafts, and we're different than just having rebuilt components. So what we do is we have teams of highly skilled tradesmen, and instead of just replacing wear items within these components, they get taken down all the way to their cores. And we have sometimes there's transmissions that OEMs like Allison will make updates to over several decades of tuning that platform, and we'll throw the old cores into our CNC machines, make those updates ourselves, and actually provide our customers with a product that beats OEM specifications. We have around 46 locations, including storefronts, distribution centers, and manufacturing. We also have a little over 1,150 employees, and we're all associate owners at Weller Truck Parts. So fun fact, we're the 27th largest ESOP in the US. So what that means is when anybody in the company can find ways to reduce downtime, improve efficiencies, or save money, all of us benefit from it. As far as the infrastructure perspective goes, we are heavily on-prem with about 98% of our workload existing on-prem in 2 data centers. We have somewhere around 1,200 cores, 16 terabytes of memory, so we're not very large compared to a lot of the other companies that have shared some interesting stuff here the past couple days, but our primary users of our data centers are actually our coworkers. So we have a couple public-facing applications, like an API that we use to pull data into our website and check availability and take orders. But for the most part, they serve each other, the associates at Weller Truck Parts. So the problem that we are running into is, I think, one that a lot of companies with an architecture like us, where your primary users are everybody inside the company, you have on-prem data centers, it's really easy to kind of get comfortable with your secondary data center. And for a lot of people, they just leave it as a cold site. I think it's really easy to go out and buy, there's a lot of options for top-of-the-line backup appliances, and you can do storage replication and slap a plan together for doing restorations, maybe test it, and find that it takes 30 minutes, an hour, 4 hours to do a recovery in an emergency. But for me, I didn't really feel that was efficient use of our resources, and I didn't think that we were netting our company the most profit or serving our users the best. So I wanted to move to an active-active workload for every application that we could. But the question that I was running into is, if we run an identical workload at both data centers, how do we efficiently monitor them, and how do we direct users to the correct data center that we intend to? Naturally, we use the load balancer. But some of the decisions and questions that we were talking about before settling on the load balancers are, we were looking at what other companies were doing, and there's options out there that make this pretty easy with VMware Site Recovery Manager or Zerto. But the big issue with those traditional products are they are like a recovery mechanism. So you're still going from data center A, maybe marking your storage offline at data center A, marking it active at data center B, and then you can boot up and write to those volumes and use that workload. So the failover process is far from instantaneous with those solutions. A bad idea I had when we were brainstorming this about a year ago was going to be to solve this problem with DNS. And a very bright colleague of mine stopped me. Not that anyone ever has issues with DNS, but it just didn't seem like the cleanest way to handle it. So we asked ourselves, what are many of the other large companies doing to handle this problem? Now I know, like, for example, Netflix places all their nodes at the edge of the internet, and they peer directly with internet exchanges, and they're using layer 3 stuff like that. And it seems like that was one of the most efficient ways to do this. So we were strongly looking at Anycast DNS, and that's what we ended up settling on. But we had to ask ourselves, what happens if the data center goes offline? Are we going to be depending on resources at any specific data center? What's the behavior if those are down? And we wanted to make sure that whatever solution we chose could scale easily and that we were minimizing the opportunity for more human failure. This I didn't know this is actually a meme local to West Michigan. So there's some protesters downtown one day, and this just kind of turned into a template. So our goal, we wanted to implement a world-class architecture for availability and failover. But I wanted to make sure that over the next 10 years, we didn't have to redesign this and re-architect this over and over. That we had some flexibility so we could put any workload we wanted behind the solution. So the big ones, obviously, VDI, but REST APIs. But to have the flexibility to take any layer 4 application and put it behind the solution was important to me. I also didn't want to have a human sitting in the driver's seat to conduct a failover. So that way we could leverage things like health checks and make those decisions automatically and spend our time investigating the root cause and alerts instead of making sure the traffic moved over. Lastly, I wanted to maximize the efficacy of our IT budget. Being that we looked at quite a variety of load balancing solutions, I was really shocked at some of the pricing. So when we were able to land with HAProxy and get the Enterprise Edition with Fusion, we had ample amounts of funds left in the budget to focus that money on other critical components like routers and firewalls. So let's get into the implementation a little bit, or what the solution was that we came up with. We began with kind of a SD-WAN solution that was giving us some problems, so we had a prerequisite to actually eliminate that, and we migrated all of our locations to next-gen firewalls. But we made sure that all the network components we were introducing into our data centers would use open routing protocols, so we would get the most control and flexibility possible using things like OSPF and BGP. We took our happy nodes then, and we peered them directly to our core routers at both data centers, and then used the RHI module to inject Anycast BGP into the network. So essentially what we're doing is we have front ends for identical workloads at both data centers, and they're the same IP addresses that can be reached with multiple paths. The next thing we did was we managed the solution with the control plane of Fusion. It really simplified a lot of the configuration and monitoring, and things like Request Explorer have been amazing. Then all the workload that we wanted to add to the solution, whether or not we were actually load balancing the back end and placing multiple servers in the back end for scaling. If it was a single server, we still placed it behind HAProxy Enterprise, so that way we could get that route health injection. Lastly, we didn't want to reinvent the wheel, so anywhere possible in the back end, we leverage native clustering technologies. So things like DFSR, Windows failover clustering, SQL clustering, a lot of that has simplified the actual failovers between the two data centers. And the benefits of the solution we came up with are that we are able to respond a lot more rapidly to data center issues, and they occur at the network level. So we don't have to sit and manually click buttons and monitor, making sure workloads are moving between the two sites. It also significantly eases patching. We can take a server down in the back end during the middle of the day, patch it, bring it back online at the opposite data center, monitor it, and then move on to the next one. No one has to stay up till midnight anymore updating those. Putting the servers behind HAProxy also gave us the benefits of Fusion, very improved monitoring. So if you've used things like Nginx or Apache or IIS, I think most people can probably agree that all those native logging mechanisms are atrocious, and it's just a pain to grep through text log files and stuff. So when you're able to visualize them, it just makes it a lot easier to understand what's going on. And the last benefit of the solution, which has been huge for us, and I've heard quite a few other customers mention it today, is that the support team with HAProxy is just amazing. I think a lot of people in this room are familiar with the same old song and dance where you go out and you buy some fancy new product and it may cost hundreds of thousands or even millions of dollars depending on scale, and you run into your first issue. You open a ticket with the vendor and it just takes weeks to get the ticket escalated to someone that actually knows what they're doing. And it's probably the worst part of my job when that happens. But every time I've opened a ticket with HAProxy, I've been met with some of the smartest, most intelligent people I've interacted with. They've got very great knowledge of how the product works, but also all the underlying systems in Linux, in IP tables. So we've been able to resolve issues very rapidly, and they've been patient enough to help me even with stupid questions sometimes. So this is a brief overview of kind of how we use Fusion here. If you're not using it already and you're using HAProxy Enterprise without the Fusion control plane, I highly recommend upgrading and using it. But what I'm going to show you is what we typically see in our Request Explorer is something like this. On the right-hand side, you'll note that everything's hunky-dory. We got response codes 200 on all of our API calls. But one morning, I migrated one of our web applications. It runs on iPads. I migrated it behind the load balancers, and users were getting intermittently signed out. We had the web application firewalls turned on because they come with it, so why not? But I noticed when this issue occurred was we were really quickly able to see what the cause of the problem was. We are hitting a deny filter on a web application firewall. So trying to understand what's actually going on inside of your applications takes a lot less time when you have resources and graphs and beautiful layouts that show your termination states like this. Now, if you're anything like me, I much rather prefer to talk about the technical things than business-related decisions, but I want to go into the configuration here a little bit, and I'm going to show you in a very few slides that you don't have to be a mega billion-dollar company or a FANG company to have world-class availability within your applications and network. Myself and a team of 4, we are able to physically go to all of our branch locations, swap network hardware, migrate subnets over, deploy the load balancers, and test applications in under 6 months. So they really make it pretty easy to use the HAProxy products. Within our configuration, like I mentioned, what we're doing is using Anycast BGP. So we have 2 identical environments at both data centers, and they're receiving routes or applications through the HAProxy Enterprise nodes. We added a MPLS interconnect between our data centers for syncing syncing backend data. And then every router and firewall within our network runs BGP now, so they're all in their own autonomous system numbers, and it lets us distribute those Anycast routes down from the load balancers to all locations around the US. While we were in there, we also opted to route all traffic from the branches into the data centers too for things like SSL decryption, central inspection, and security policies. This is a visualization then of what our BGP network looks like, but what you'll note here is we have a prefix reserved 10.200.20.0/23, and then inside of there we have Cedar 32s for all of our front ends. Those come down from our cores at both data centers to border firewalls, to another set of firewalls acting as SD-WAN hubs, and then to our branch firewalls. And what we end up with is a really nice solution for actually scaling out and adding additional data centers for a deployment like this as well. So if you notice on the left and on the right, we end up with a really clean stack top to bottom. And we have plans of opening a data center out towards the west region so we can service our associates in the west side of the US with lower latency as well. All we need to do is just get another pair of load balancers in there, cores, firewalls, and we're done. We can just start injecting those routes from Denver or Las Vegas at any time. What we did to peer our load balancers with the cores is we used Bird, which in HAPI, I believe, is called HAPI Extras RHI, but it's essentially Bird. And we peered using OSPF to get loopback reachability with our cores. And then over the loopback addresses, we use BGP to inject the route health information. Another thing to note is we also enabled BFD, or bidirectional forwarding detection. If there's anyone not familiar with BGP, there's a condition where if your peer actually goes down, the default behavior means it could take up to 30 seconds for your peer down to be detected. So this isn't things like route updates, but if maybe you lose power to a load balancer or the underlying host running it, or a severe critical networking issue, by forwarding, bidirectional forwarding detection allows you to bring that detection time down from like the 30-second area to 100 milliseconds. And you can actually go lower with more configuration, but we're just doing 100. This is what our Bird configuration looks like then. So you can see we have a couple BGP processes used to peer the load balancers directly with the cores. And you'll notice at the bottom of those sections, you see export where proto equals vol1. This is the volatile table that the route health injection module will store the routes in when applications are up or meet the conditions that we set. Then at the bottom left corner there, to turn on BFD, all you have to do is you can create an empty little bracket there, and that enables it. And then you can start it with the overlying process. So by adding BFD or BFD graceful into your BGP configuration, that enables that signaling for BGP. The OSPF stuff is pretty simple. We're just advertising the loopback address into the core, and we have the area attached to the physical interface and the loopback interface. Now, some notes for enabling these features on Ubuntu. I just found out yesterday this is going to get a whole lot simpler with their new appliance release, so the point may be moot. But the documentation does cover all this excellently if this is something that you want to try to reproduce or do in your environment. You need to add some static routes on the loopback interface. You have to also add another socket, which you could put right in your global config of Fusion for the RHI module to access your runtime API. And then you have to make some rules to intercept that traffic because the operating system doesn't have a IP address on any of those interfaces when you have transparent IP addresses on your front ends. And this is what the RHI configuration actually looks like. So the first demo that I'll show you here in a bit is actually this top one, but you're just meeting a condition here. We're saying inject 10.200.20.1 into the BGP peer if any server in the backend called web farm is online. And if everything's configured correctly and you have your front ends and back ends set up, you'll see something like this when you do a show route on the HAPI route CLI. So you can see that these routes are sitting in our volatile table already. If your router that it's peered with is properly configured, they'd be sitting in your routing table as well. One thing that I want to note too when I distribute these routes is I use prefix lists with the default deny rule at the bottom so we can get really good control over what routes we're sending to what routers within our network. You have to enable BFD on your peer end as well. So on the right-hand side here, our neighbors 10.200.100.5 and 100.6 are our load balancers. And you can see we have failover BFD there. And then we also have some route maps attached to that. We're using 2 different route maps for our bringing the routes into the cores, because originally we deployed this without using equal cost multipathing. But once we got our stick tables behaving the way we wanted to, we can actually eliminate that now too. For the magic sauce now though, if you do this at both data centers, you might still ask yourself, well, how do the clients or the other routers know what data center to go to reach your applications? There's a few different influences on path selections within BGP, but 2 of the most dependable are local preference and path length. So what we're doing is we're going to our Indianapolis data center and we're artificially making the AS path longer by prepending it 3 additional times with the AS number of those core routers. What this looks like then from the branch location perspective is we have identical routes at both of those sites. So we're at a branch firewall right here looking at the routes, and you see the top ones here all end in 65,001 going to our Grand Rapids data center. But then you also see some on the bottom that are a little longer, and they have 65,002 prepended on the end there. Now for some fun. I have a pre-recorded demo that I'm going to use as an opportunity to kind of pause a few times and walk everyone through what's actually occurring during one of these failovers. And I also have a demo that we're going to do in our production environment as well. So what we have right here is just an IIS server, and you're going to see the welcome to Indiana within that image to let you know that the IIS server is being served from Indianapolis. And if we look at our firewall here, we see the asterisk flag next to that route that ends in 65,002, indicating that the application is being served out of Indianapolis. What we're going to do is go to the Fusion control plane then, and we will actually mark the application as ready in the Grand Rapids data center. And this occurs very rapidly. So if you know, we have a timer running in the corner here too. So we mark that as online, go back to our web browser, hit refresh, and now we're connected to Grand Rapids. This is obviously the simplest of demos because it's just static content. So depending on what type of applications you put behind this, you're going to need to think about stuff like authentication and cookies and how you synchronize those within your backends. And then there's a couple simple scripts here running that are going to get paused real quick. What the one on the left is doing is it's running a trace route every 1 second. And the one on the right here was running a GET request every 1 second. In the middle of the screen on the left, if we look at hops number 3 and 4, we watch those change at the 1 minute 55 second mark to 1 minute 56. The hop beginning with 10.194 is in Indiana, and after we failed over within HAProxy Fusion, you could see that change to 10.190, indicating Grand Rapids. But then on the right-hand side here, we are making a GET request every second, and we didn't miss a single response. So we'll take a look at what this looks like now from the branch perspective again. We'll refresh our routing information base here. And now you can see that that route ends in, or that AS path ends in 65,001, indicating Grand Rapids. So all this can occur and propagate within your network extremely rapidly. Depending on how you architect your applications, these failovers can be not noticeable to your end users at all. All right. Now, what we're going to do is illustrate another test of this using our VDI environment, which is probably, I would say, maybe our most critical application that we use at Weller Truck Parts, because associates have to be able to log into their desktops to run our ERP, take orders, know what to build. And in this example, what we're actually going to do is leverage the health checks that are configured in HAProxy. So we're going to disable our connection servers on Horizon and let HAProxy detect this. that's another thing to keep in mind when you're doing a deployment like this, is that your health checks play a big role in how long it takes to detect a failover and how quickly that actually takes place. Little background here. I'm going to show you what this will normally look like if we're running out of the Grand Rapids data center. I can open the Horizon client here, connect to our VDI environment, and I'm presented with an option of desktop pools. Most users will typically only be assigned to one at a time. But what happens if the Grand Rapids VDI environment goes down? Well, we can do that real quick. So what we're going to do is disable our internal connection servers. And now we'll check out Fusion. See if I can find it here. Yeah. Go to our Grand Rapids cluster. And we're going to wait for the health checks to fail. So the servers that say Gambit and Sabretooth are both going to turn red. After that happens, we're going to see exactly what occurred with the IIS server example. The health checks will fail. The route health injection module will stop injecting the route to Horizon at Grand Rapids within the network. And then we'll reconnect to our Horizon environment again, and we'll see a completely different selection or options for our pools. And we can actually log in there, and all of our user data will still be there because it's synchronized at the back end with something called FSLogic's Cloud Cache. So let's check on these. So it looks like one of them's down. We'll find out if they're ready to go already. There we go. We're at our DI or DR VDI pool, so I can connect to this. Their user will log in like normal. Probably won't notice any difference because all their user data is still going to be there. There it is. Now, how do we monitor the solution? Monitoring the environment is really important to us because it's gotten a little complex and we need to know what's going on at all times. What we ended up doing, can we go back to the slides? What we ended up doing for alerting is all of our happy nodes are sending log data directly to Fusion, obviously, but we also send that to a Graylog server where we have a couple queries running every 5 minutes, and we're sending email alerts and opening up internal help desk tickets if a BGP change is detected or an application server goes down. And then another thing that I wanted to do was be able to show all the routes in the volatile table without having to SSH into one of our happy nodes every time and run the command myself. So we already had a pre-existing Zabbix environment, and I wanted to leverage that since it's already sitting there. So we put the Zabbix agent on our load balancers. And there's a parameter in the configuration called user preferences or user preference. And what it allows you to do is create a new variable name and then have a command that the Zabbix agent runs. So we just made the Zabbix agent run the show route for us, which lets us get little lists. They're real time, so we can just go to one of our dashboards here, see what applications are getting injected by the network, and then infer what data center is running that from there. So some of the caveats we encountered as well are we ended up just turning off automatic updates because we had, like I said, we had a couple extra packages added to the virtual machines, and there were a couple instances where the automatic updates actually rebooted or restarted the HAProxy process, but then the route health injection module got stuck and needed to be restarted as well. Came into work one morning at 6 a.m. and trying to figure out why every application was running out of Indianapolis. There was updates. The next thing was logging within Fusion. We ended up using HTTP CLF logging instead of TCP logging. you have one option to use for the Request Explorer. So the support team was amazing helping us get some custom formatting applied to our front end on our Fusion configurations. So that way, when we go into Request Explorer, we can see the combined logs for both types of applications, HTTP or TCP. And then another issue we ran into is some MPLS providers won't advertise multiple paths for the same route. This is default BGP behavior, and some vendors won't turn on something called add path for you. So that's something to think about if you leverage MPLS in any of your backends. There's some workarounds like multi-hop BGP, but for now we're just living with it. And then another issue, if you use HAProxy for firewalls or any type of SD-WAN, I'm sorry, not HAProxy. If you use Palo Alto for any type of SD-WAN solution within your environment, we are using Panorama with the SD-WAN plugin module, which essentially just generates tunnel configuration for all your devices in your configuration. But what they do is they generate unique community strings that get appended to your BGP routes. That took a minute to figure out as well, but you have to add those community strings to all these routes you want to distribute throughout your environment if you want those to go to your branch locations. Some of the lessons learned in terms of improving infrastructure reliability. Anycast is an extremely efficient way of directing users to specific data centers and for scaling out your environment. And hot sites are the best way to optimize your disaster recovery resources. If your application's failing over, you already know that there's probably a problem. So having HAProxy handle it yourself means you have more time freed up to actually investigate the root cause of issues. Next, being able to manage all these configurations in a single control plane massively simplifies stuff. Some of the homebrew stuff I was thinking about cooking up meant that we'd have to be constantly comparing configuration files in 4 locations, and it was just not a good idea. So when you can log into Fusion and manage all your clusters from a single location, have all your log data aggregated, it just simplifies your life. Another big lesson learned was that using your network layer for data center failover is a lot faster than DNS. And I know a lot of people do use DNS for stuff like this, but you're dealing with things like local caches, clearing those, and also propagation time between DNS servers within your environment. Then the last thing for infrastructure reliability is implementing native health checks within all your applications. Means that once you have the solution deployed and tested, it's fully automated. In terms of choosing HAProxy specifically, we looked at, like I said, a couple different vendors for load balancers. HAProxy not only was the fastest, but it seemed like it was the easiest to configure as well. And every time we can simplify our lives, it means that we're more efficient and we can spend time on other projects. Another thing with HAProxy is they made it really easy to deploy their product quickly. Like I mentioned, I have a relatively small team. You don't have to be a giant organization to be able to deploy something like this, and you don't have to be massive to benefit from it either. And that's all I got.
Awesome.
Thanks.
Great, thank you, Austin. So we do have time for a couple questions. Again, if you'd like to ask one in the room, just raise your hand up nice and high and wave so that I can see you. We did have a couple that came in the stream.
Okay.
So the first one is, what advantages does Weller get from managing multiple data centers and interconnect versus putting it all in the cloud?
Good question. So like I mentioned, we have somewhere around 1,200 cores. If you take a look at the cost, I figured that it would be somewhere around $90,000 to $100,000 a month minimum in compute. So if you're running your own hardware in data centers and you have the team to support it, there are massive cost efficiencies. With the cost of running something like this in the cloud, we could rebuy the hardware twice a year.
Another one from the chat. So this actually was maybe related to what you just said, but what was your cost savings you saw compared to your previous disaster recovery solution?
Oh, I wouldn't say that there were really any cost savings because before we just weren't doing it. We had a way to restore backups, and we had a well thought out plan. But if disaster really struck, we'd be waiting 4 hours or so while that workload is spun up. Maybe you get blessed with some Microsoft updates or something. So yeah, we weren't really doing the same thing before.
Awesome. Well, thank you so much, Austin. Appreciate it. Give it up for Austin.